My name is Jürgen, and in this seminar, I will present the new GeoDict 2026 release and show highlights and new developments. So we will look at the new features sorted by business area. At first, we look at general improvements in image processing and image analysis. Next, we move to the filtration business area, going from the filtration to the electrochemistry field. And we now look at improvements in the digital material R&D. With this, we come to the last business area, the digital core analysis. And at last, another feature of general interest. And we have invested not only effort into developing new features, but also in improving the documentation. And in addition, there's a new learning center on our website that collects all available material in one place. So there you can find the user guide, but also the tutorials and the online seminars. These slides have been prepared with contributions from many of my colleagues. Let me first introduce myself. My name is Jürgen, and I am the head of Mass to Market support team. Before I co-founded the company in 2011, I worked at the Fraunhofer Institute of Applied Mathematics, which I joined after finishing my studies of mathematics at the university in Bonn. Before I come to the highlights of the new version, let me say a few words on GeoDict in general. What is GeoDict? GeoDict is a software featuring a digital material laboratory that lets you do multi-scale 3D image processing, modeling of materials, visualization, material property characterization, simulation-based material development, and the optimization of physical processes. The GeoDict workflow is usually like this. You collect data from a microCT or another imaging device and load it into GeoDict. You apply image processing to segment the data into a structure model. You can then run simulations directly on this model. Plus, you can generate a digital twin and apply simulations to the actual part and digital twin variations to better understand the material performance. Let me illustrate this workflow in our software. So you start with a three-dimensional gray value image. Here, as an example, a fibrous material. See here, this is a gray value image of a 3D dataset. You can look at it in various directions, from the side, from the top, and you see here the 3D preview. You then have to turn these gray values into material information. So that means you have to decide which voxels belong to fiber, in this case. This is not always straightforward, and you need good tools for it. So here, for example, the fibers look hollow in the image, but in fact they are not, and you need AI to get a good segmentation here. Once you have done the segmentation, you have a 3D model of your structure in the software. You can look at it, and you can also run simulations on it. So for example, you could use GeoDict to compute the pore size distribution of the material. But of course, you're not limited to the pore size distribution. You can also do any other type of analysis here. So this digital material solution is needed in different business areas. Filtration, electrochemistry, which summarizes battery and fuel cell and electrolyzer materials. In digital material R&D, where we consider composites, foams, non-wovens, and granular materials. You can use it to do digital core analysis on rock core samples. And you can use it for image processing and image analysis for all kinds of materials. This is needed in all business areas, but it's also an application on its own. So we have now finished the new major GeoDict release. So this happens annually, and we name the version after the year in which the software is distributed. So this new version now is called the 2026 version. The new version is ready now and available for testing. And the official release will be in the beginning of January. So every 1 or 2 months, we will release a service pack that contains bug fixes for the various modules. These service packs will be named then Service Pack 1, 2, 3, and so on. They do in general not contain new features, but a number of bug fixes, and therefore you should always install them when they become available. In this talk, I would like to show the feature highlights of GeoDict 2026. And one of the features is already visible on the right side. It is possible to use the dark color mode in the GeoDict user interface. So we will look at the new features sorted by business area. At first, we look at general improvements in image processing and image analysis that are useful to all the business areas. For this, I'll switch back to the software. When you want to segment these data, you can do this either by selecting a gray value threshold that distinguishes between pores and fibers. If this is not directly possible, for example, if the gray values, like in this example here, inside of the fiber, have the same values as those inside of the pore, you have to train an AI to understand what is pore and what is fiber. And to do that, you have to label some parts of the image manually, and then the AI can learn from you and do the rest automatically. And of course, this approach is not only applicable to fibrous structures, but to any type of material. And there are now a number of improvements that make this labeling easier. First, if you want to label, you select the material you want to label pore. And now we have the new Lasso mode here. So you can directly label a large part with this new Lasso mode here and segment these parts as pore, which helps to speed up things. Then you also have the magic brush. This was there before in previous versions, but it's now much faster. The magic brush means that you have some pre-segmented area, and then you can go quickly and, for example, mark this. And now, if you have mistake, we have a new undo, and you can also switch this back. And I also did the mistake that I wanted to label this as the solid material. And then, okay, I can go along this fiber and mark things as solid rather quickly. And yeah, this helps in segmenting these parts. And now if you see, okay, you have done some mistake, you can do the undo again, which wasn't there before. So let me summarize. For the AI labeling here, we have now undo and redo. We have the lasso mouse, and we have optimized the magic brush. Plus, in cases where you have two 3D image sets loaded, the labels can be kept when you switch between those images. So that makes the labeling much quicker and easier to use. Additionally, the new version supports a direct import of DICOM files. Previously, you needed to use other tools to convert the DICOM files into something that GeoDict could import. Now you can directly load them into GeoDict. Coming now from the import to the export of materials. Sometimes you want to use models created in GeoDict in another software. Until the current version, many CAD formats required the use of an additional tool called CutLook, which had to be purchased from another vendor. And now in the upcoming release, this will no longer be necessary. We have integrated a more powerful open source library into GeoDict. It's called Open CASCADE technology, which allows export of step and IGES format. So now you can directly export the objects like grains and fibers. And it's also possible to export the pore space instead of the solid space. And to demonstrate that, I load an example file. And show how this can be exported into a CAD file. So you find the new feature here in Export GeoCut. And now there's this new entry here, Export Object Cut. And there you can choose directly the step and IGES format as output. And if you do that and export the files, then you can, as soon as it's written, open the step file into any CAD program. For example, here for demonstration, if I open it in FreeCAD, which is an open source tool that allows to look at CAD files, then you can just see the same structure as solid objects here in this tool. But of course, you can also load it into ANSYS or any other tool that you have installed. So next, we move to the filtration business area. Before showing what is new, let me summarize how GeoDict is applied to simulate filtration. Filters are everywhere, and so there are many different setups. You may want to filter aerosols out of the air or dust particles out of oil or water. The filter materials can be quite different as well. Non-wovens, wire meshes, or ceramics, depending on the use case. So typically in GeoDict, we look at the microstructure of the materials and simulate on the filter media scale. But it's also possible to upscale the materials and simulate the complete filter or the filter element or a pleat. In the last years, we also started to look at adsorption processes as they are relevant for activated carbon filters. The GeoDict can model adsorption was a new app in the 2025 version. And this has now been fully integrated into GeoDict 2026. In the 25 version, we introduced a particle or tracer-based solver for adsorption and desorption processes. And the simulation first computes a velocity field using the standard flow solver, and then particles are tracked to the velocity fields. And the adsorption process is simulated using isotherms like Langmuir or Toth, which predict how particles are adsorbed into the adsorbate at the interface. In GeoDict 2026, the runtime was improved for fast chemical reactions using an adaptive time stepping. In addition, a more advanced reaction solver implementation leads to increased stability and precision, especially for fast reaction. Also in the previous version, we introduced a field-based transport solver in BatteryDict capable of simulating advection and diffusion processes. And this solver computes the concentration fields and breakthrough curves by discretizing both processes for each voxel. Now in the 26 version, the field-based transport solver is also capable of simulating sorption processes. And it can simulate adsorption and desorption processes in porous media and predicts the solute and sorbate concentration per voxel for each time step. So it couples advection and diffusion equation together with reactions equation and solves the time-dependent problem. Similar to the tracer-based solver, it supports different isotherms like Henry, Freundlich, Langmuir, or Toth. And here you can see an example where the transport solver was applied to simulate adsorption of CO2 into zeolite in a packed bed reactor. CO2 is injected from one side with a given concentration and transported through the pore space, and it's adsorbed in the porous powder. Currently, this field-based approach takes more time than the tracer-based approach, but we are working on a speed up for this kind of simulation. And I also want to show where this new feature is available. So I load an example, the packed bed reactor file. And you can see here, this is a structure generated with GeoDict, where we have piled spheres into this cylinder. And you can switch off here the cylinder so we can look at the inside by making the cylinder invisible. And the features, the new ones, have implemented into BatteryDict. So we have here now a new command, adsorption. And this allows to use the new solvers, both the tracer-based and the field-based approach. So here comes the dialog. So here you can choose which of the solvers you want to use and set the boundary conditions for the solver. As usual, on the constituent material tab, you define the material properties and the porosity, tortuosity, permeability of the porous materials. So really the new thing now here is on the Adsorption tab, where you can define the properties of the adsorbate and of the adsorbent. So here on the adsorbate tab, you can set the input concentration, partial pressure, molar fraction, whatever you want to choose. You have to define at the inlet how much of the adsorbate enters the simulation. You can set an initial value or load an initial field as starting conditions. On the adsorbent tab, you can define in which material the adsorbate is adsorbed, and you can also set an initial loading. And last but not least, on the interaction tab, we have different isotherm models that you can select off. And if you don't want to use a model but have experimental or measurement data available, you can enter them in the form of a data table. Once you have set the parameters and let the simulation run, which I'll skip now for the sake of saving the runtime, you will get a result file that will show you, the used isotherm, but it will then compute the breakthrough curve. So it will show you at which time 5 or 50 or 95% of the inlet concentration is reached at the outlet. And you will get a report of the total uptake of the adsorbent. And of course, like always in GeoDict, you can load the results at any intermediate time step. So for example, you can load the concentration at some intermediate time, say, and look at the concentration on the porous materials. And then we have the concentration and also the loading of the sorbent pellet with the adsorbate. And yeah, we can visualize the status at any intermediate time step. So another highlight achieved in Filtration last year was a general validation of the filter efficiency simulations for electrode air filters. And in this validation project here, we looked at 6 different electrode materials. All the materials were imaged by micro-CT and imported into GeoDict. We simulated the filtration efficiency for these materials, both under the assumption of a discharged filter media and under the assumption of a charged filter media. And at the same time, measurements were done by our partner, the IUTA Institute in Duisburg, where the efficiency was measured for the original charged material and after discharging the material in isopropanol. And as we can see here, the simulation results here, the solid line matches very well the experimental measurements, which are these dashed lines. And in all of the cases, both for the uncharged and the charged material, the simulation is somewhere in the spread that we observed when we repeat the measurements. And this worked for all the 6 materials. So we proved here that we can reliably predict efficiency of electrode filters. Another exciting feature, which will get more important in future versions, so in the GeoDict 2027 and beyond, is the ability of the Lear solver to refine and coarsen the computational mesh over time. So, as you may know, the solver uses an adaptive grid to discretize, for example, velocity and pressure. And currently, this adaptive grid is constructed based on a geometry and refined later based on the computation. But the solver could not coarsen grid cells again when the accuracy is not needed anymore, which happens in time-dependent problems. And this will now change in GeoDict 2026, where this will be applied for all the time-dependent simulations, like we have them in BatteryDict already when we do the field-based transport solver. And the feature will also get important when we simulate transient Navier-Stokes equations in FlowDict. So this is not possible with the 26 version, but you can see here some experimental code or experimental prototype for the transient Navier-Stokes solver. And here on the right, we see the carbon vortex street computed with transient Navier-Stokes equation. And we see how cells are split and merged beyond the spherical obstacle. And this is some ongoing development that will probably be available already in the 27 or a later version. But you can see that we're working on solving also time-dependent Navier-Stokes equations, which would let us solve not only stationary problems, but also get in stationary solutions for larger Reynolds numbers in the future. So, going from the filtration to the electrochemistry field. And with electrochemistry, we will today focus on battery electrode materials. For these, you can determine geometric properties like porosity or pore size distribution, as you can do this also for other application areas too. You can also derive transport properties of these materials, again, as you would do it in other application areas. What is special for battery materials is that you can use BatteryDict to simulate charging and discharging of the battery. And these battery charging simulations, you have the option to do it with the fully resolved microstructure model. So this is somehow the classical GeoDict approach. And here you model the transfer of the lithium ions and the intercalation of these ions into the active material on the full 3D structure model that resolves the particles, the binder, and the electrolyte-filled pores of the electrode materials. But it is also possible to upscale to a homogenized model where the electrodes are described by a 1D Newman model, which takes effective parameters computed on the microstructure as input. And in this case, the charging simulation is just using the simplified model and runs very quickly. BatteryDict got many improvements in the GeoDict 2026 version. One major topic was to implement features into the Lear solver that were previously just available in the best microsolver. And this was done because the Lear solver is computationally more efficient and therefore preferable. But you were only able to use it if you did not require one of the special features that only the best micro could do. And now you can always use the Lear solver and benefit from the increased efficiency. And that lets you use less computational resources for the fully resolved model, because you can now always use the Lear solver. And in detail, the Lear solver is now able to compute and write additional fields into the volume files, namely overpotential and plating potential. It computes the heat production in the post-processing, and it can also handle concentration-dependent parameters for active materials and electrolyte. The Lear can consider these concentration-dependent active materials and electrolyte properties. And this slide here shows a benchmark where the Lear and the best simulations are compared on this large NMC structure. And this is a structure that was shown at the GeoDict Innovation Conference in 2024 by Adrian Lindner of the KET. The electrolyte and the NMC 622 in the cathode structure here are modeled with concentration-dependent parameters, shown here. And then the results are shown on the right side. And we see here that both the Lear and the BEST, they compute the identical results. But the Lear has, just about half of runtime. But the real benefit is over here in the used RAM memory, so we can reduce it from 190 gigabytes to 8. And this reduction in memory is extremely helpful because it may be the difference between you're able to compute a solution or you're not able to compute a solution with your given hardware. Another feature that brings BatteryDict closer to measurements is the new boundary condition to prescribe a voltage range. So in a real charging or discharging experiment, the cell voltage is kept within a certain range, for example, between 3.2 and 4.2 volts. And this is done, for example, to avoid cell damage or fast degradation. And in GeoDict 2026, you can define a lower and upper voltage bound for BatteryDict simulations. So for example, you can see an example here at the bottom where the equilibrium curve is shown for the mentioned voltage bounds. And you can see here a screenshot of the BatteryDict GUI where you can enter this voltage range. In addition, there's a new simulation mode that's called Calculate Equilibrium Potential Curve, where you can quickly compute this equilibrium curve based on the current constituent material properties. And so you can expect the voltage windows covered by the open circuit potential of the active materials. And in many application areas, it is also required that you charge or discharge a battery with a constant power instead of a constant current or constant voltage. For example, when you charge a battery, the maximum power that the charging device can deliver is restricted. And also when you discharge a battery, the cell voltage is usually not constant, but decreasing over time to maintain a constant power. And in the 26 version, it's now possible to prescribe a constant power boundary condition that allows charging and discharging of a battery with constant power. But we also improved the homogenized model. So when performing a best meso simulation with the charge battery command, the calculation of parameters required, diffusivity or conductivity, takes most of the runtime. So if you want to perform multiple simulations with best meso with different input parameters like C rate or voltage window, then BatteryDict used to determine the same parameter again and again, which leads to a waste of runtime. And the 26 version now offers a new feature to overcome that issue. So first, a new mode in the charge battery command called Calculate Homogenized Parameters was introduced for calculating the effective parameter like diffusivity or conductivity of the material. And then in the second step, you can use the new charge homogenized battery command to quickly vary the experiment parameters or to vary the geometry. Geometry meaning you can set the outer geometry, not the microstructure geometry, but the size of say the anode thickness or separator or cathode thickness. And in this way, the command lets you quickly perform multiple homogenized battery simulation where you can vary C rate or voltage window, something like that. And there's a new Geo app now into BatteryDict that's called Battery Capacity Test. And this script allows to predict the accessible cell capacity of battery structures for varying charging rates or voltage windows. The script runs one or multiple charging and discharging simulations using a specified protocol. And using the script makes the capacity test simulations much easier. You can, of course, also do all the steps done by the script by hand using the charge battery command, but this prescribes the parameters typically used and makes the setup of such a test much quicker and easier. And there's also one feature that I want to show now in the live demo. What we have also now implemented is the electrochemical impedance spectrum simulations, or in short, EIS. So with this type of simulation, you can predict the complex valued resistance called impedance of electrical components like a battery. And the EIS simulations can be performed on battery and electrode structures. They are computed directly on the fully resolved or the homogenized model. And for this, the solver is controlled with a special charging profile over time, and the response is then analyzed in the post-processing step. And as a result, you get the complex value resistant, called IGES, and this is typically plotted in these Nyquist plots that show for varying frequencies the real part and the imaginary part of the impedance in this 2D plot. You can also plot that with these Bode plots that we have also here now. This feature is currently only available in the best solver and accessible through expert settings. But we will make this more easily accessible through a Geo app in a later service pack. So that were the improvements for the electrochemistry area. And we now look at improvements in the digital material R&D. What we mean with digital material research and development is shown in the workflow on this slide. It often starts with the import of a 3D image of a real material. You then analyze this image to understand the material and its properties. And if you understand the material geometric properties, you can create a statistical digital twin. And having this twin, you can start to design or engineer a next generation material with improved properties. But sometimes creating a digital material fails at the very beginning, because you don't have any 3D data available. And if you don't have them, it's difficult to start the whole process. And here the next development may help. So usually 2D images are widely available and much easier and cheaper to obtain than the 3D microcity images. And in GeoDict 2026, an intense effort was made to improve the generate granular twin from 2D GeoApp. And with this app, it's possible to create a 3D digital twin out of a 2D image. So the app takes a 2D segmented image as input, as well as some options for the structure generator. And then it runs some optimization loop to find the best parameters for the 3D structure generator, so that the properties of the 3D generated material match the one of these 2D slides. You can see here in an example, this is the segmented 2D image. So, and then we run the app and end up with this 3D material. And we then can compare the 3D with the 2D material and see how good this matches for the data that we are looking at. And this is an option that makes it possible that you create digital twins for some materials where it's very hard to get 3D microcity images, but you have some SEM images available. Another example is the dense sphere packing generator in PackGeo. Here, the generator was optimized and works now more robust, even for complicated sphere size distributions. The code was optimized and parallelized. So now it's possible to use multiple cores for the structure generation. And you can see here a benchmark. If you increase the number of cores used from 1 to 16, you can gain a speed up of factor of 5 in the generation of this type of sphere packings. Yeah, and with this, we come to the last business area in today's presentation, the digital core analysis. Here, everything is centered around rock core samples taken from a drilling site. So you can digitalize these samples with microcity and load them into the computer. And then GeoDict can be used to determine various properties digitally. Porosity, pore size distribution and permeability, grain size distribution, relative permeability, mechanical properties, and up to considering fracking or carbon capturing and storage. And here, often multiple fluids are present in a sample: oil, water, gas, and the distribution of these fluids should be predicted by the simulation. At this point has now seen an improvement. So previously, the surface tension could not be taken into account for computing the fluid distribution. It was just used as a scaling factor for the capillary pressure computation. So now in the new version, we have the capability of considering viscous and capillary forces in subtlety. So the capillary number, which is computed by the viscosity times the contact line speed divided by the surface tension, can now change the contact angle used in the simulation. So there are two contact angle models implemented, one for liquid gas and one for liquid-liquid two-phase flows. And both models take as input the static contact angle and the capillary number and yield the advancing or receding contact angle. And an example can be seen on the right. On the top, you can see that the capillary number of 0 leads to the same contact angle in the small and wide pores, but we get a different contact angle in the small and wide pores if we have a capillary number larger than 0. And you can see this clearer even in this animation, where we go from small to large contact angle with a kind of constant filling rate. So this means from step to step it slows down, and the angle goes from almost 90 degrees to something like 45. Yeah, another feature is the pore network model, which is available in the identify pores command in BatteryDict. So this command offers a new capability to compute and save the network of pores. So if you have sandstone like this, you can create a pore network model that consists of balls that represent pore bodies and connectors that represent pore throats. And you can make up this model of balls and connectors and export them as a pore network model for other softwares. There's also a new Geo app designed especially for digital rock physics, the Acoustic Rock Properties Geo app. This app allows to predict seismic properties of rocks, which are the P and S wave velocities. So assume that a rock as shown here on the left side. So typically such rocks consist of grains with different shape and diameter. And these grains are not perfectly connected. But the mechanics solver usually models perfect contact between the grains. So there's a perfect stiffness there. And this leads to overestimated stiffnesses and wrong P and S wave velocities. And this app now has a special pre-processing step where the individual grains are identified and the interface here between these grains is marked. And the grain-grain contact will then get a lower stiffness compared to the grains in the elasticity computations. And this allows for an accurate computation of the elastic properties for the P and S wave velocities. The predicted wave velocities then assign values that are reported in the literature. Yeah, and at last, another feature of general interest. So the job queue was introduced in GeoDict 2024 and allows, like the cloud capabilities, submitting GeoDict jobs to a large remote job queue server, which executes jobs one after another. And in the 25 version, the job queue got a lot of improvement already to provide greater control and visibility. But now in 26, there are two exciting improvements. So the first one allowed much better utilization of a large shared memory machine. And it's now possible that the job queue server can launch and execute several jobs in parallel. So it's no longer just a single job queue, but you can run several jobs in parallel. So for example, imagine a large machine with some 192 CPU cores. Then with the new feature, you can run 6 jobs in parallel, where each job runs in parallel itself with 32 cores. And the second new feature here is the support of priorities and queuing in the license system, which is also important for standard floating license environments. So previously, when more than one user wanted to use a floating license, it was random which user got the floating license first. And now there's a clear first come, first serve principle. So the first user who requests the license will get it first. And it's also possible to assign priorities for individual computers. So for example, you can prefer the job queue server over the laptop when it's about who gets the license first. And yeah, in the past slides, I have shown many new features in the upcoming 2026 version. And we have invested not only effort into developing new features, but also in improving the documentation and creating some training material. We have in the last year converted the user guide from PDF documents to an HTML website. And this allows much easier search through the whole document. And all the user guides for the 25 version are already available, and the update to the 26 has already started. And in addition, there's a new learning center launched on our website that collects all available material in one place. So there you can find the user guide, but also the tutorials and the online seminars, like this one here. And you can download also additional material there, but you have to register, which simply means you have to leave us your email address, and then you get an individual login to the learning center that you can use to download material. And with this, I thank you for your attention, and hopefully see you next year in the next online seminar again. Goodbye.